Welcome to the Experts in Sport podcast, brought to you by the School of Sport, Exercise and Health Sciences at Loughborough University.
Welcome to another sports performance themed episode. I'm Stuart McErlain-Naylor and I'm joined today by Dr. Mark Burnley, who is a senior lecturer at Loughborough University, specialising in the physiology of endurance exercise. Mark recently published an invited review article on the speed-duration relationship across the animal kingdom, and he's going to be talking to us today about what athletes and humans in general can learn from others in the animal kingdom. Hi Mark, welcome to the Experts in Sport podcast.
Hi there.
Really looking forward to this actually. So, well, bit of maybe related background. Had a recent interview with Franco and Pellizzeri about training load monitoring in elite athletes. But Franco was really passionate about the idea of sports science learning from other disciplines. With him, it was all around what we can learn from medicine and take that into how we study athletes and sports science. But I'm really interested in the work you've done around the animal kingdom in general and what humans and athletes can learn from other animals, maybe. So I think we'll come back to that a bit later on. But to start with, I wondered if you could just give me and the listeners a bit of a background into, I guess, your background, the expertise you bring, and how you came to be reading and writing about various relationships across the animal kingdom, really.
Yeah, so my fundamental interest in sports science is exercise physiology, and particularly endurance physiology. And I was trained to study the kinetics of oxygen uptake, so looking at the dynamics of the oxygen uptake response to exercise. So from rest to exercise, what happens to oxygen uptake at different intensities? So if you're doing low intensity exercise, something different happens from when you do high intensity exercise. And so that was my postgraduate training, and that was what I did my PhD on. And I got really interested in the notion of the power-duration relationship, critical power, and the physiology surrounding that concept. But as a result of studying oxygen uptake kinetics, I got to know very well one of the leaders of the field, David Poole, and he was doing some really fascinating work on the exercising thoroughbred racehorse. So at Kansas State, they'd got themselves an equine treadmill. They'd sorted out a gas analysis system. They were able to take blood samples and muscle samples from the horse. And what they'd essentially done is they'd got a stock of ex-race horses, which would otherwise have just been sold into private ownership. And they had a stables there where they were able to take several of these racehorses and do a number of experiments related to race performance. So the question of why is it that horses bleed into the lungs when they're racing? Is there anything you can do to mitigate that? Because that would then extend the lifetime of the horse and the racing time of the horse, that kind of thing. And that's kind of got me. It was interesting at the time, but I didn't really think much more of it because I was completely focused on humans. And then I went to Aberystwyth to teach there, and it just so happened that they were trying to start up an equine and human exercise physiology degree between the what was then the Department of Rural Sciences and the Department of Sport and Exercise Science at Aberystwyth. And it meant that we had to then integrate human physiology and equine physiology. So a lot of the exercise-related things we were doing was done in the human physiology laboratory, but most of the students we had were equine students who were more interested in the horse. And so to sort of sell it to them, we had to then translate that to what this would look like if you actually did the exercise in a horse. How would it differ, and those kind of things. So that got me really interested in just that cross-species comparison, which brought me back to the work of David Poole. Anyway, time went on, and I kept interested in it and looking at comparative physiology. And as part of my lectures to undergraduates and postgraduates on the power duration relationship or the speed duration relationship, it became quite clear there were other animals that had been studied in a similar way, which were really quite varied. So a researcher called Bob Full, who was working out of the University of California, Berkeley, did a series of experiments with a lucite chamber and a very small treadmill. And he had all kinds of creatures which had interesting anatomy and physiology. And he was studying their exercise responses. And one of the things he made sure he did was look at their endurance capacity across a range of different speeds. And of course, what that does is produce the same sort of speed duration relationship that you can see in a human if you do a series of different length races. So it meant that we had some data that we could compare, for example, a crab with a salamander, with a gecko, with a human, with a horse, etc. And that I found that really interesting because they all sort of fit along the same sort of curve shape. And again, I didn't think a great deal more about that until I was asked last year to write a comparative physiology paper by a friend of mine, Craig Sale, and he had a colleague working out of Brazil who was interested in putting a series of papers together in comparative biochemistry and physiology, the journal. So I said yes, and I decided to frame that on the speed duration relationship. So that's really how it all started, and that's what led to me then publishing a paper on the comparative aspects of the speed duration relationship. So we studied obviously humans, horses, dogs, rats and mice, crabs, lizards, salamanders. We then went on to study fish and also birds as well. And it's quite difficult to do that because there isn't really the way fish are measured in the laboratory are completely different to the way humans are. We'll probably come on to that later. But also birds have never actually had their speed duration relationships measured before. They've had their oxygen uptake measured before, but they've never had their endurance capacity measured. And again, there's various reasons for that, but it turns out that birds are so good at endurance that it's difficult experimentally to put them in a position where they're actually going to be so fatigued that they stop flying. So it led to a really interesting series of, well, why is that? Well, why does that happen? How has this animal managed to exploit its own niche with the cardiovascular and respiratory systems and muscular system that it's actually got, which differs from the human, and how does it differ? And then the real trick is to then let that swing back to, okay, well, we've learned all of that about this animal. How does that reflect back to the human? So what I was really doing there was sort of the opposite of what I was doing with the equine degree, was starting with the animal and then trying to work my way back to see how that related to the human, if it related at all. So by choosing the right animal model, what you actually have is a situation where you can essentially look at the models you're studying in humans, but look at it in the extreme in a particular animal model and see why it's so extreme. And you can then kind of explore the physiology from there. It just becomes much more exciting doing it that way.
If one of those key models or relationships is the speed duration relationship that you mentioned a few times, kind of in simple terms, I guess, what is that? Or why should I care about that? You know, if I'm a human, well, which I am, or an athlete, why should I be interested in the speed duration relationship?
So, yeah, I mean, in general, the speed duration relationship simply describes the speed you are able to run or swim, or if you're using power, cycle for a given duration. So if let's just take a couple of examples. Let's say you have an elite athlete. Let's take an Usain Bolt. Now, we know that he can run 100 meters in less than 10 seconds. So that's more than 10 meters per second. But if you then asked him to run 800 meters, he'd run that much slower. So he might not run that at much more than 6 meters per second. And what you do is, in the laboratory, what you do is you set speeds and then you exercise people to task failure. So you literally put them on a treadmill and you set them at, let's say, 5 meters per second as a treadmill speed, or, you know, if you wanted to do it in kilometers per hour, 17 kilometers per hour. And then essentially what you do is you exercise them on that treadmill, you start a stop clock and you keep them going at that fixed speed until they can no longer maintain speed with the treadmill. They have to slow down or stop. So on a treadmill, you have to grab the handrails and jump off and jump astride the treadmill. And then you take that time for however long it is, and then you run at a faster speed and a faster speed again. And what you do is you construct a curve from those exhaustive exercise bouts. So it takes 3 or 4 days to put that curve together. But what it then gives you is 2 really important measures. So we have what we call the asymptote of that relationship, where the curve starts to curve towards infinity. So you end up with a particular speed that you can theoretically maintain forever. and that's called your critical speed. Now, we know that doesn't really work in practice because humans will always run out of energy at some point. But what the critical speed tells us is it gives us a boundary between exercise we can do in the steady state and therefore not be fatiguing versus exercise where if we exercise above the critical speed, we do exercise which is in the non-steady state. So you cannot stabilize the physiology and everything basically goes haywire. So if you're exercising above your critical speed, you will become, or you will reach task failure eventually, or become exhausted eventually. And if we do several exercise bouts above the critical speed, we can then calculate what that critical speed is. And then we can work out where your steady state and non-steady state domains of exercise are. And that can be really important for an athlete if they're training because it helps set up training zones. But it also helps us understand what physiology would we expect. So if you're exercising below the critical speed, you will probably be doing marathon or half marathon running. So that's the kind of intensity you're working at there. If you're working above the critical speed, that's your 10,000 meters, 5,000 meters, 3,000 meter type races where it's high intensity, you can't stabilize anything, and eventually you're going to have to slow down. So pacing strategy there is really important. If you go much faster than that, we have the sprint events, which still fit along the same curve. They don't fit very well. But really and truthfully, what we also have is another parameter which is related to those sprint events, which is what we call the distance prime. It's a measure of how far we can run above the critical speed before we have to slow down or stop. And that's a fixed distance. So you can either do it really quickly, in which case you'll fatigue rapidly, but you'll run at a fast speed, or you can eke that capacity out slowly if you exercise just above the critical speed. So say your critical speed is 4 meters per second. If you ran at 4.2 meters per second and you had a distance prime of, say, 300 meters, then there'd be a length of time over which you'd be able to eke that out before you reach task failure. Whereas if you ran at 8 meters per second, you'd use that up much more quickly. And that curve shape then helps athletes with their pacing strategies because they know when they can surge and when they can ease off. And you can also recover that capacity by exercising below the critical speed. So if you've ever watched a 10,000 meter race on the telly, you probably would have seen people surging and then recovering, and the lap times will change dramatically from one lap to the next. And that's what they're trying to do, is put people in difficulty and use up that distance prime in their competitors to try and get away. If that doesn't work, they just relax back into the bunch. They might run behind somebody. That also reduces the oxygen cost and therefore reduces things below the critical speed again. And then they can build that capacity back up again and then surge again. And so one of the reasons why there's a sprint finish at the end of a 10,000 meters is because they're husbanding that, if you like, that capacity. So the distance prime has been likened to a battery that you can use fast or slow above the critical speed. So that's how it sort of fits in with athletes. And then the question becomes, well, what physiologically determines the critical speed? What physiologically determines the distance prime? And I've mentioned the aerobic, anaerobic side of things. The critical speed seems to be quite well correlated with the amount of slow twitch muscle fibers that you've got. So slow twitch muscle fibers are the endurance fibers. They fatigue very slowly. So the more of those you've got, the higher your critical speed will be. You can also train critical speed. So by doing endurance training designed to increase your aerobic capabilities, you will increase your critical speed. Distance prime seems to be more related to not so much the amount of fast twitch muscle you've got, but in terms of the amount of muscle mass you've got. So if you think about if you've got more tissue with more energy in it, you're going to have that bigger battery. So one of the ways of improving distance prime is by strength training. Another way of doing it is by loading up with creatine monohydrate. That's been shown to increase the distance prime as well. So those things that increase the size of that battery, if you like, which are related to anaerobic potential, that can also help improve the distance prime. So that's really how those things work in practice.
Okay, so that all makes sense. Yeah, it's really great to see the kind of tangible examples of like the pacing strategies, and I think it's quite clear, or it's clear to me why that's useful to know and why those parameters are really useful to know and manipulate or try and improve. But then why do we need to know, or why can we benefit from knowing about animals? Kind of, if we already know, if I know what those parameters are for me, how does knowledge of either bigger or smaller animals help me in any way? Are there things we can learn from that help me in my training design, or is it kind of, learning maybe the limits of what might be possible through human performance?
Yeah, there's a couple of answers to that. I mean, first of all, the comparison itself is just fascinating. So to put things in a completely different sphere and see if they still work or not is fascinating in itself. The other thing is we can think about, well, do different structures that animals have, they might have different ways of breathing, they might have different cardiovascular systems. How can we then look at the margins of human performance and try and manipulate those as well? We could also see where animals are limited compared to humans. So the obvious example is the lungless salamander, which has the lowest critical speed ever measured because it doesn't have any lungs and it has to breathe through its skin. So there's diffusion limitation there. But that then tells us something about disease. So if you have lung disease, then you have an inability to respire and take up enough oxygen. And that lung limitation, of course, is not dissimilar to having a limitation of not having any lungs at all. So you can start to see parallels between both high performance animals and low performance animals. And I'm not necessarily suggesting that the lungless salamander got it wrong, because that's what evolution is. And the salamander's been around for 65 million years. So it's doing something right. But it also tells us that the way evolution seems to work is that for most animals, it's about energy cost minimization. Whereas as sports scientists, we're all about energy cost or energy transfer maximization for sports performance. We try and run fastest, jump highest, run for longest. Animals don't really care about that. They just want to be able to eat, sleep, mate, and survive. So it's not really about how fast can I run unless it has to be. So unless you're being chased by a lion, you don't necessarily need to run fast. So a salamander, which lives in leaf litter most of the time and eats insects, doesn't have to run particularly fast to be able to carry on eating and that kind of thing. But in terms of what it also tells us about humans, we can talk about horses and how they operate, and the fact that we have a really, really well-developed cardiovascular system in the horse. And the horse is definitely lung limited. So it has to breathe through its nose. And because of the way in which it gallops, its stomach contents are constantly bashing up against the diaphragm. So it can only breathe once per stride. That means it needs a very, very good buffering mechanism, because it cannot use its ventilatory system to defend itself against a drop in pH. So it can't defend itself against an increase in blood acidity during exercise. So it's got an enormous carnosine buffer in the muscle. So proteins within the muscle that are there to soak up hydrogen ions. And interestingly, that has led to beta-alanine supplementation in humans, because beta-alanine is the precursor of carnosine. So it's led to a whole sports supplement industry born of our understanding of how horses are both lung limited, but also then solve the problem of being lung limited by changing its buffer capacity in the muscle. So ways and means of dealing with potential exercise intolerance in animals can lead to performance changes and dietary changes in humans, for example. So there are all kinds of weird pathways that you can see that appear because of our understanding of a particular animal species.
How do we know these things? I'm very familiar with the idea of a sports science lab or a physiology laboratory. Someone running on a treadmill, we might be, as you said, manipulating the speed they're running at. We might be kind of measuring oxygen expiration, etc. What does that look like for athletes? You mentioned kind of salamander, horse, other examples. Are we putting those on some equivalent of our sports science physiology lab? Or how are we taking those measurements? How are we controlling what they do and actually measuring how long they can sustain performance, I guess, at those different speeds? Because I imagine it's not as simple as put them on some kind of device and see how long it is before they get off, or push the stop button.
Yes, it's It's not quite as simple, but you'll be surprised that it is actually almost as simple. In the same way that, if you take somebody who's never run on a treadmill before, they'll be a bit unsteady to start with, so you have to habituate them to that. So you normally, and that's one of the reasons why cycloergometry is such a popular mode of exercise for cardiopulmonary exercise testing in a clinical setting, because you don't have to train somebody to ride a bicycle or turn pedals. Whereas on a treadmill, it becomes a bit more difficult. So you have to habituate them to it. So you might take the first session of just getting them used to jumping on and off the treadmill, using the handrails, knowing where the emergency stop button is, that kind of thing. You sort of do the same thing in animals as well. So you just get them comfortable with being in that environment. And the environment itself, if we take the equine treadmill, for example, it is fundamentally just a very, very large treadmill, and not bigger, but not dissimilar to some of the treadmills you would have seen. For example, the Peter Harrison Centre will have large treadmills that are designed to run wheelchairs on. And the equine treadmills are not dissimilar, because they have to be very large, have to have a large belt, a wide belt. They obviously have to have enough motor power to be able to sustain a horse galloping on it. And it has to be able to be inclined. But other than that, it's a treadmill. It's just a very large treadmill. The next thing you have to think about is, well, how do we take actual physiological measurements from these animals? And in terms of blood parameters, it's relatively simple. You use the same sort of catheters that you'd use in a human. You just put it into the horse's jugular vein in the neck. And the nice thing about horses' veins is they're very big. So it's not like you often struggle to get a line into the vein in some people who just don't have very prominent veins. You never have that problem with a horse. It's actually relatively easy to find. Although I've never done it myself, because I've not worked directly with horses. I've been told it's pretty easy to find those things. The next thing you need to be able to do is measure oxygen uptake. And in humans, we either use a face mask or a mouthpiece and nose clip to be able to do that. And then we have an off-the-shelf gas analyzer that we can basically measure oxygen concentration, carbon dioxide concentration. Then you need some kind of flow measure, normally a turbine or a pitot tube or a pneumotac or something that can measure how much air is going in and out of the lungs. We can do the same sort of thing with a horse. But because they are obligate nasal breathers, we can't simply fit a face mask to the horse. What we have to do is essentially put them in a large tube attached to their head, much like a bridle is. So it's a little bit like if you've ever seen a horse with a nose bag with oats or something in the bottom of it so the horse can eat. It's a little bit like that, but it then has a very wide tube coming from it. And at the end of that tube, there's a fan, and that fan is drawing air past the horse's nostrils. And at the end of that, beyond that fan, you've got the gas analyzers. So they're actually sampling the air that is running past the horse's nose. And as the horse breathes out, it will dilute that air with extra carbon dioxide and less oxygen. And from that, you can measure that. And because you know the rate of flow of the air going past the horse's nostrils, and you can also calculate the changes in oxygen and carbon dioxide given that flow rate, you can calculate the oxygen uptake of a horse. So it can be done. It just takes slightly larger tubing, shall we say, in the horse. If we go to the other extreme and think about some of the animals, like we've mentioned the lungless salamander already, essentially all you need there is a very small treadmill and a lucite chamber where you know what the concentration of the gas going into the chamber is. You then measure the concentration of the gas coming out of that chamber, and you can calculate the salamander's oxygen uptake. There is a slight problem with measuring things like lactate, particularly in things like crabs. You can't take a fingertip blood sample from a crab because they have claws, and you can't really get past the chitin in the claws, which is what makes them so strong. So unfortunately, if you're going to do these sorts of animal experiments, and when Bob Full did these experiments, he took a measure of whole body lactate, which is, as the name suggests, at the end of the experiment, the animal was taken out of the lucite chamber. It was then snap frozen in liquid nitrogen, the whole animal. It was then broken up with a pestle and mortar and then put into some liquid. And then you extracted how much lactate was actually in the whole body itself, the whole body space. So essentially the whole body fluid. That's only an experiment you can do once, of course, because you can't put the creature back together again, unfortunately. But that was the way it was done. So like I say, it's similar, but different and a little bit more difficult. For fish, you can use a swimming flume, which is essentially an enclosed flume. You don't need to worry with humans with a swimming flume. You basically have essentially a pool that humans jump into, and then there's some kind of propeller driving the water past the human. The same sort of thing happens in fish, but you keep it enclosed. So you then have a pump working the thing around. You can also have a probe in there that measures the oxygen content of the water that's running past the fish, and you can then calculate fish oxygen uptake if you really want to as well. So that's how it's done in fish. And in birds, you can use a wind tunnel. And believe it or not, you can train a bird to wear a face mask. It's been done in budgies, it's been done in gulls, and it's been done in geese as well. So you can miniaturize these things to such an extent that birds can fly whilst wearing an oxygen uptake face mask. And so that has been done. The problem with that, of course, is that there's only a finite number of animals for which this has been done, and for which it can be done. Because if you took, for example, a dolphin or a shark, we might like to know about their exercise performance, but it's actually very difficult and virtually impossible to measure oxygen uptake in those creatures because they're just so large you can't get a space big enough where you could sample the oxygen from. So what happens a lot of times in these creatures is we tag them in the wild, or in the case of dolphins, we can use dolphins who are in large aquaria, the Sea Life Centre or what have you. You can actually measure them doing laps of their pool, but it won't be a faithful reflection of what they do in the wild. And of course, because dolphins and other whales as well have a dive thing, you can't really measure their breath by breath oxygen uptake because they might breathe only once every 30 minutes. So it then becomes very difficult to measure oxygen uptake during exercise because they are fundamentally holding their breath. So that becomes difficult. So in reality, we've managed to measure the animals we can measure. And alongside that, we have dogs, which you might think are pretty easy to measure because they're man's best friend, for example. But actually, dogs are quite hard to measure on a treadmill because although they're quite obedient, they're also quite curious and inquisitive creatures. And there are other interesting things going on in the laboratory that distract them. So there was a PhD student who spent 9 years trying to measure oxygen uptake in ex-racing greyhounds, and he managed to do it in 1 out of about 70 greyhounds he was given because all of the others refused to either wear the face mask or run on the treadmill for long enough. And he had to have the treadmill really steeply inclined at about 7 to 10%. And he then had to have a plastic bag at the end of the treadmill so that the dog would actually try and run towards it. He had to keep flicking that bag as well. He managed to get about 60 to 70 seconds worth of data out of 1 greyhound in 9 years. All the others would just jump off the treadmill or refuse to wear the face mask. There have been measurements made in Alaskan Huskies. So those sled dogs that do the really extreme ultra endurance work. But when you're looking at those dogs, it's probably better to use doubly labeled water to measure energy expenditure anyway, because they're exercising over such a long time rather than measuring oxygen uptake with a face mask. That has been done. And we think that these dogs have a VO2 max of about 200 millilitres per kilogram per minute compared to a normal human's 45. So that gives you some impression of the scope there. Horses are around the same level. Pronghorn antelope, which we think is the fastest endurance animal on the planet, it can cruise at about 65 kilometers per hour, about 18 meters per second. It has a maximal oxygen uptake of about 300 milliliters per kilogram per minute. And again, it's been measured in the same way. There are other creatures which are probably almost as good as the pronghorn. So we've been able to take measurements of running ostriches, which have the advantage of having the same sort of physiology that other birds do, which is very, very good at consuming oxygen, and kangaroos as well. And kangaroos are special because they store so much elastic energy in their tendons that they don't really increase their oxygen uptake as they run faster and faster and faster. So We haven't measured the speed duration relationship in those creatures, but that would be really interesting to do because I think they'd come out with some pretty high values for critical speed, for example. So overall, you can do it. It's difficult in some cases, sometimes impossible, but the ones we've managed to do it on, I'm pretty confident that the data we've got is both accurate and meaningful physiologically and in a performance context.
The story of the greyhounds probably fits a lot closer to my imagination of testing animals. I know people say never work with animals or children, but that's pretty much what I was expecting. I'm actually really surprised that that doesn't seem to be the norm with all the other animals as well. So how does that issue of either motivation or, I guess, actually with a human, you're saying run on a treadmill, cycle on an ergometer, etc., maintain this intensity for as long as you can. And it's almost a kind of psychological thing of how long can I keep this going before I have to jump off or press the big red button. With animals generally, is it more a case of, it might not be this simple, but kind of, eventually you'd fall, if there was no big red button, you'd fall off the back of the treadmill. Is it some aspect of setup where the animal doesn't have that much choice about whether they're doing it or not, and ultimately they will keep going until, well, I guess they either give up or can't possibly keep going any longer?
It's a great question. I think the answer is it's a survival of the fittest issue. So animals generally are, trying to survive, and so their survival instinct is to keep exercising. And if you give an example of the way in which you would do the speed duration relationship in a rat, and this is another set of experiments that David Poole has done. Obviously, the rat is a really useful model for all kinds of human disease and human physiology studies, because they breed quite quickly and you do all sorts of various knockout experiments with their genetics and all kinds of other stuff. So knowing their speed duration relationship and their exercise capacity, in relation to things like cardiovascular disease is really useful, because you will constantly intervene and give a rat an experimental dose of chronic heart failure, for example. So taking measurements of rats on treadmills is quite common. And so there are protocols in place to make sure that you get the most out of your rat. And the way you do it humanely is you run them on a treadmill and you keep blowing air at their hindquarters, because that is essentially a stimulus to say, there's a predator behind me, I need to keep running. And they will keep running until they stop. And when a rat stops running, it literally turns over and lies on its back. So it's essentially, I'm done, let's get it over with. And they literally show their belly so that whatever is chasing them will give them a quick death, essentially. And that is the best sign of task failure in a rat, that it's basically given up on life. So you're pretty sure that rat is exhausted, because otherwise it wouldn't do that. And there are other, this same thing happens in crabs, actually. So the ghost crab, when it's been measured, we'll come on to talk about that in a moment, I'm sure. When it's actually exhausted, it will first drag its belly and then it will turn over. And you can also see various color changes in the crab, which indicate that it's reached the limit of tolerance. So, and essentially the same sort of thing is true of a horse. I mean, with a horse, you can give it gentle encouragement by essentially shaking a whip behind it. You don't hit the horse with the whip, but you can by swishing a crop or a whip behind the horse, it will carry on galloping on the treadmill until it can't gallop any further. And there's clearly a safety issue with half a ton of animal falling off the back of a treadmill. So there are harnesses, and there's a band at the back of the treadmill where if the horse goes onto that band, it will immediately disconnect the treadmill from the power. So it will stop immediately and the horse will then stop galloping. So, there are safety measures in place for that kind of thing. But fundamentally, animals want to keep running from a survival perspective. So we don't have to worry too much about their psychology, because they will keep going.
Yeah, obviously, without talking about 200 different animals, are there any general trends of the speed duration relationship or any other relationships that map onto kind of, body size or body mass or different characteristics of the animal? I'm kind of picturing graphs in my mind where you've got lots of different animals plotted on the graph and kind of looking at general trends where maybe without measuring some new animal, you can kind of guess some aspects of that relationship based on how they compare to others. And I guess I'm also wondering if those kind of relationships do exist, where do humans fit within that? Are we kind of an extreme at one end, or are we pretty average right in the middle?
Yeah, so there's a couple of ways of doing it. The key difficulty is that there's sort of a bimodal distribution of animals that have been measured in this sense so far. So we've got humans, horses at one end, and then we've got ghost crabs, lungless salamanders, geckos, lizards at the other, which are very much smaller. So we've got one group of animals that's measuring critical speed in meters per second. And then we've got another group of animals where critical speed is being measured in centimeters per second. So, and obviously that is due to the difference in animal size. So as with any comparison, you want to rescale things, because if you think about bacterium to blue whale, you've got animals that vary in size by several orders of magnitude. So how do you then fairly compare between animals? And one of the ways of doing it is by using the speed duration relationship and calculating the ratio between the two parameters. So you essentially take your distance prime, you divide it by your critical speed, and that gives you a measure of the time you would take to run at twice your critical speed until exhaustion. So as an example, a human with a critical speed of just over 4 meters per second and a distance prime of around 250 meters would have about 60 to 70 seconds of tolerance at double your critical speed before you had to slow down. A horse, which had a critical speed of about 14.5 meters per second, that'd be an elite racehorse carrying a rider, they would be able to gallop at double their critical speed, nearly 30 meters per second, for about 18 seconds, so much smaller. But that's because the horse is a very, very good aerobic performer. It has a relatively small distance prime. At the other extreme, you've got the painted ghost crab, which is a very good aerobic crab performer by crab standards, but it also has a very, very large distance prime. And so its ratio between distance prime and the critical speed is about 470 seconds. So it's absolutely enormous compared to other animals. And it makes it arguably the best middle distance runner in the animal kingdom. So if you gave a human being a ghost crab's endurance parameter ratio and you were able to run at twice your critical speed for 470 seconds, most humans would be able to comfortably run a mile in less than 4 minutes. In fact, they'd run a mile at nearly a mile in 3 minutes. And if Eliud Kipchoge had the ghost crab's physiology and so Eliud Kipchoge's critical speed is 6 meters per second, we think, from measurements that he's had prior to his marathon performance. His mile time would be 2 minutes and 13 seconds if he was, if he had the same physiology as a ghost crab. So in that spectrum of different ratios of distance prime and critical speed, humans are pretty much in the middle, which is actually where you'd expect them to be, because humans are basically metabolic non-specialists once they're in adulthood. Children tend to be pretty aerobic. They can run about forever and don't seem to get tired. Whereas as you go through puberty and you put on more muscle mass, you tend to go in one direction or other. You emphasize the endurance side of things, or you emphasize the strength side of things. And if you have a little bit of both, then you become a team games player or something like that. So we tend to be non-specialists. We don't tend to excel in any particular feature, but we can train these features to be slightly better. Or, if we want to kind of emphasize endurance, maybe make our strength slightly worse so we're not carrying that mass around unnecessarily. So that's actually a good thing for humans to be in the middle somewhere, because our survival hasn't ever really depended on us being very good at exercise, to be honest. There's a school of thought that suggests that humans are much better endurance runners than other animals, and we used to be able to hunt by persistence. So we used to chase down antelopes. We'd carry on running until they became exhausted. I'm not sure I buy that as an evolutionary thing, because there's no real sexual selection in that. because when you've ever seen that still does happen in certain parts of sub-Saharan Africa. Some tribes still do this, but it's a very inefficient way of capturing meat compared to, for example, standing at the edge of a river and throwing a rock at a fish. It's much easier to capture protein in that sense because you're also close to a fresh water course as well. So having the guile to catch a fish and thinking it through and cooperating is probably what developed humans as humans, and therefore developed our brain power and our dexterity to be able to use tools to do these sorts of things, rather than develop any physiological attributes that made us really good at endurance or really good at speed. So that probably explains why humans are stuck in the middle of this kind of speed duration relationship balance.
Is that 250 metre value you mentioned for humans distance prime, is that one of the reasons why the 400 metres is so brutal and such a hard race?
Yes, it is. So if you think about a 400 metre runner, they will probably have a distance prime that's bigger than 250 metres because simply the way they train, but it's probably not as big as 400 metres. And even if it was, in order to be that big, you've got to produce a lot of energy anaerobically. So you will produce a lot of lactate, which is not necessarily fatiguing, but alongside that, you produce a lot of hydrogen ions. So you'll make your muscle very acidic. You'll use your sodium potassium pumps an awful lot. And what that will do is change your interstitial potassium concentration, which we know is fatiguing. You'll also very significantly increase your inorganic phosphate concentration in the muscle, which we also know interferes with calcium, which is what's responsible for activating the muscle in the first place. And you will, as a result of all of that, you will very, very quickly start to slow down. All of those things will, and particularly the change in pH, will also stimulate ventilation. So if you've ever seen the interviews at the end of a race in the athletics coverage, they're always gasping for breath. And that's because they're trying to deal with all of the load that they've put on themselves during that 400 meter race. But yes, it also means that your energy stores are limited and you have to rely partially on aerobic metabolism, even in a 400 meters. Otherwise, you're simply not going to finish at the right speed. And it also explains why you see so many people slowing down at the end of a 400 meters. And it's fair to say that the winner of a 400 meter event is the one that slows down the least. So it looks like somebody's accelerating away from the rest of the pack. It's not the case. They're all slowing down. It's just the person winning is slowing down less fast than everybody else. And it's quite interesting to see that play out. And it was really interesting in the World Championship of Athletics in Budapest this year in 2023. A number of athletes actually stumbled towards the finishing line. So, Bol, the 400 meter runner from the Netherlands, fell over without anybody touching her at all. So you could actually see her stride very quickly shorten up, and then she was unable to correct herself and she fell over. That is almost certainly due to this build-up of anaerobic metabolites in the muscle, and the muscle being unable to essentially respond to the nervous input that she was giving at that time, because she wanted to win the race. Her muscles just wouldn't let her at that point. That's fatigue writ large, and that's because she would have come pretty close to utilizing her entire distance prime at that point, and therefore she had nothing else to give, and she would have had to have slowed down then.
And now I'm going to give you the chance for a bit of myth busting, but is it not due to the accumulation of lactate within the muscles?
We think not, and the reason we think not is because what lactate is basically half-burnt sugar, essentially. So it's a very useful metabolite because it can then be shuttled around to various parts of the body, can be used by the brain or by the heart muscle to actually then release the energy that's still in that particular molecule. And there were some really fascinating experiments done in the early part of the turn of this century in Denmark. Was it Denmark or was it Sweden? One of the two. I think it was in Copenhagen in Denmark. And basically what they did, they got rat muscle and they fatigued the muscle by pumping it full of potassium. And then what they did was they pumped 20 millimoles per litre of lactate into the muscle. Now, for the listeners, 20 millimoles of lactate is what you would see at the end of a maximal sprint. And they pump that into the muscle. And by pumping that lactate in, muscle force recovered. So in that sense, lactate was protecting the muscle against fatigue. So what we think is lactate is a marker of high intensity exercise, but it is not in itself a cause of fatigue. And actually an increase in lactate during exercise might protect the muscle from some aspects of particularly fatigue associated with the inability to carry the electrical signal through the muscle to activate the muscle. Lactate might protect against that failing. So it might actually be a protective thing rather than a fatiguing thing.
That makes sense. Now, are there any other examples you can think of that either have been done or that maybe should be done in the future of where human performance could benefit or learn from the animal kingdom? So I'm thinking, study of animals to figure out how to run fast, like study the cheetah to figure out how to run fast, study a kangaroo to figure out how to jump, etc. Do you know if these things have been done, or can you think of any good examples within your area of physiology where actually there is a lot more we still have to learn from looking outside of just human performance?
Yeah, so and again, we'd probably go back to the horse, and I've already mentioned its buffering capacities, but with the horse in terms of cadence entrainment of its running and its stride length and its breathing frequency. Entrainment of breathing cadence is something else that the runners have worked with, and how frequently you breathe when you run, because that can also prevent things like stitch. Most runners have pretty much got that off pat now anyway, so that's an interesting one. You mentioned the cheetah, and you've also mentioned the kangaroo. We've already learned those sorts of things many years ago about the stretch shorten cycle and trying to maximize that. So that's led to things like plyometric training to try and improve that the kind of bounding things that you do. And that has a number of benefits and potentially also a number of problems, because the bounding that you do can be quite damaging. So you've got to be a bit careful with how you introduce that, because you are essentially stretching these biological materials, and sometimes you might stretch them to failure. But it also then allows you to activate the muscle in particular ways, which might then become more efficient if you do them more frequently. So the bounding of a kangaroo and the storage of elastic energy and becoming coordinated enough to be able to do that could benefit performance. So understanding that from the animal model certainly has translated into the human. The cheetah is an interesting one because it's always noted as the fastest animal in the world, but the cheetah is actually not that good at hunting prey, because possibly 1 in 10 hunts are actually successful. And in hunting, the cheetah actually in the middle of the day, it gets very, very hot very quickly. And as a result, it has to catch its prey before it essentially cooks itself, because its core temperature rises very rapidly. So one of the things obviously humans have been very interested in is how we exercise in the heat and how we then recover from that kind of thing, pre-cooling and those sorts of things. It's not directly related to the cheetah, but the cheetah is an extreme example of what can happen if you exercise too intensely. So thinking about how we then advise athletes to exercise in the heat, how they pace themselves in the heat, that kind of thing, does translate from those sorts of queries and those sorts of investigations.
And then I have one final question that's been passed on to me. So our regular host, Martin Foster, says he plays football with a guy that often refuses to warm up, and his excuse is that lions don't warm up in the jungle. Any comments or kind of in response to that? So
yeah, lions don't have to. Well, first of all, lions don't live in the jungle. That's probably the first thing to say. They live in the savannah usually. The savannah is also quite hot, so why would you necessarily need to? Lions certainly don't stretch as such. There's a question mark about whether stretching would be worthwhile doing as part of a warm up. Because if you've been doing heavy training and you've damaged the muscle already, why would you stretch something that's damaged? The other thing about stretching is it can reduce maximal strength. So you've got to be a bit careful about how you structure a warm-up. But there's a couple of things I'd say. First of all, we know from cold-blooded animals such as lizards, they can sit on a rock and warm themselves up, and they can double their VO2 max doing that, and they can double their critical speed simply by warming their deep body temperature up. Humans don't have that because we're warm-blooded, but muscle temperature does vary. So you really want to do exercise or passive heating that heats the muscle up if you're doing high-powered exercise. And I would argue that in football, yes, you're going to be doing repeated sprints. So you want the muscle to be warm. So you want to do any activity that actually increases muscle temperature. And if you're exercising in the heat, you might want to keep the core temperature cool. So you then wear an ice vest or something like that. But you do want the muscle to be warm, because a warm muscle is a more powerful muscle. You'll be able to kick the ball harder. You'll be able to run faster, be able to tackle harder. It will improve your performance. And in endurance sport, we know that warm-up exercise can improve performance by 2 to 3% typically over not warming up. 2 to 3% is the difference between first and last place in any athletics race. So that is a substantial gain in performance. And interestingly, we found that high intensity warm-ups in endurance sport seem to work best. So if you're going to be running a 3,000 or 5,000 meters or even a mile, you're best doing a high intensity warm-up that actually elevates blood lactate and elevates muscle lactate. Because what we think happens then is you can both recruit more motor units recruit more muscle mass when you do your next bout of exercise or your actual race, but also you can deliver more oxygen to the muscle having done that. And that's going to aid your oxygen uptake and therefore minimize fatigue as the race progresses. So that's what we call priming exercise. That definitely works. And so we found some of that out, and we also know that warming up works in horses. So for both horses and humans, pretty much any animal would benefit from a warm-up. The fact that lions don't warm up is because it's already about 35 to 40 degrees where they are anyway. So the argument would be that they don't really need to warm up, rather than warm up isn't beneficial.
Thanks, Mark. Yeah. When you listen back to this, Martin, I hope that helps. Thanks, Mark. This has been, potentially one of the most fascinating conversations I've ever had. But I think I could keep talking about this for hours. Yeah. So I think if listeners are also wanting to know more, is there anywhere that people can find out even more about your work or more about this topic in general that you can recommend?
Yeah, so the paper I wrote in the journal I mentioned earlier, we can put a link to that, I'm sure, in as part of this podcast. But that, if you want to find it, it's the speed duration relationship across the animal kingdom is the title of the paper. So if you put that in a web search, you should be able to find that. And that's where I go through all of that and cite all of the evidence associated with it. So, and there are a number of animal physiology textbooks out there, which are also worth going for. So Knut Smith-Nielsen is the classic animal physiology text. So if anybody has access to a university library, go and look for that. So there's some really fascinating things in there about, and some things we haven't said much about, things like dive physiology in whales and how that all works, and also the respiratory systems of insects, things of that nature. So, breathing through spiracles rather than through lungs, that kind of thing. So there's a lot of additional things we haven't talked about, which are equally fascinating. You'll find in books like that.
Brilliant. Thanks, Mark. And thanks once again for joining us and for, I don't know how many notes I made there, but thanks for just, such a really interesting conversation.
Cheers, Stuart. Thanks.
Thanks for listening to the Experts in Sport podcast. If you'd like to get in touch, then please contact me, Martin Foster, at m.foster@loughborough.ac.uk. Thanks for listening. See you next time.